We are.
Yeah, 4.
Don't you normally have an unlimited number of attempts?
Usually we have 2, but this will have 4, thank God.
I give you 2?
Yes.
Yeah.
Make it all already. I thought they were.
Not one has been.
There's not been a quiz that's been unlimited.
We've worked around it. I take one and then Peyton takes one. We always have 4 attempts.
That's awesome.
See, I'm fostering group work. Okay, so we've seen carboxylic acids and their derivatives. We've seen that they do one specific mechanism, nucleophilic acyl substitution. And that works for every nucleophile that is a better base than the leaving group that's already attached to the molecule. Here's the other side. So, if we let the carboxylic acid derivatives just fight to the death over who gets to be the leaving group and who gets to be the nucleophile, then our nucleophiles are negative. And whichever one's, if it's stronger than the leaving group, it kicks the leaving group off, and that leaving group is also negative. Which means that those acids are basically, that those reactions are performed in basic conditions, because I'm allowing a negative charge to be floating around. If I put this in acid, then I can't have a good strong nucleophile anymore. That means now I'm going to be doing those reactions with weak nucleophiles. So reactions in acid of carboxylic acid derivatives with weak nucleophiles. So what we're going to describe today, there's going to be a leaving group, so it's a substitution. There's going to be a nucleophile, so it's a nucleophilic substitution. But that nucleophile is weak, and the very first step that I'm going to show you is performed in acid. So it's not technically a nucleophilic substitution. That means that that rule that I made about if you were on the left-hand side of my list, you can be converted into something that's on the right-hand side of my list. That rule does not hold true any longer, because we're not doing, that's the same kind of rule that you see in SN2s. Incoming nucleophile needs to be a stronger base than the leaving group. It did not necessarily hold true if we protonate and make a carbocation, and then we're not concerned about the strength of the nucleophile. What I'm about to show on the board is something that we've almost seen before. The analog here is that. In this direction, this is Fischer ether synthesis. I'm going to take 2 alcohols and I'm going to turn them into an ether. In that direction, it was acid catalyzed hydrolysis of an ether. We've seen that reaction. That reaction has been on the board twice. First, I think, in this direction, because we turned alcohols into ethers, and then later that way. And every step is an equilibrium so it doesn't really matter. What I'm going to do is I'm going to turn my ester into a carboxylic acid. That reaction's going to need acid. Goes in at the beginning, comes out at the end. And I'm going to switch out my ester for a carboxylic acid. All right, now so technically, this still works on our framework of nucleophilic acid substitutions because esters are more reactive than carboxylic acids. But that reaction's also working backwards. So if I turn it around, now I would be doing a reaction that's impossible by nucleophilic acyl substitution. All right. Ester of your choice. What do you want the R groups to be?
Methyl groups.
Yeah, it's kind of boring when they're just methyl groups. I know it's easy. All right. Before any of that shows up, some of this shows up. Where does it go? I got those, and I got those, and I got those.
Wasn't the double bond?
Okay. Already down. Any particular reason why?
And so that oxygen can have a positive charge, and the water doesn't attach the carbon that's attached to the double.
I need to get rid of this. This carbon to oxygen to carbon bond right here, the ether part, is gone. But if I protonate it now, it's not going to leave because it's going to leave that carbon stranded. So we have to do something strange first. We're going to protonate this, that pi bond want to open, have a water attach, and then disconnect. So it makes sense to do this one. If you do the other one, if you scribble in your own private time, let me see how far I can get if I protonate that one first. Just see how far you can get. Not that far. So, are there chances that it will get protonated? Yeah. But it'll realize I can't go anywhere with that. It's a dead end, and I'll come back and deprotonate it. Okay. So I've attached a hydrogen to that oxygen. Positive charge on that oxygen. Here is where
that way up, and then it would break the double bond and get rid of the charge.
looks good. Having protonated that oxygen first, when the pi bond breaks and it moves the electrons towards the electronegative atom in that pi bond, which is the oxygen, that oxygen no longer needs to have a negative charge. So that was good. That then gives us this right here.
positive charge.
Positive charge on that oxygen. It's got 3 bonds. So I just sacrifice the 2 electrons in that oxygen to hydrogen bond onto the oxygen as a lone pair of electrons. And I get something that is common to a lot of these reactions. I get a tetrahedral intermediate. That's a lot of oxygen to be around a single carbon and everything be singly bonded. Okay. Fortunately for us, we know what we start with and we know what we end with. So this isn't us just figuring out what would my molecule like to do next. We know what the outcome is. Make that happen. What's my next arrow?
Would the lone pair of the oxygen attach to the methyl group?
I have 3 oxygens. You need to tell me which
The
one.
one on the right of the carbon. In
This
between.
one?
Yeah.
Just make this be a leaving group. Okay. Now, question arises, why that oxygen? Couldn't I just take this? That red arrow right there. Is that red arrow possible? Yes. Okay. Should I write it in as part of my mechanism?
You already did.
I already have. It's here. What about that lone pair? Already described it. What about this lone pair? It's this description. All of this has already been described and it takes a step backwards. So that's not your answer. It's already been described. All right, I just made a leaving group. Let's make it leave. What's my next arrow?
The lone pair on the oxygen. On one of the top of the
Which one?
Top.
Technically, it doesn't matter. Both of these are the same. I make a bond from that lone pair. Now between this oxygen and that carbon, I turn that non-bonding pair of electrons into a bonding pair of electrons, which are now the pi component of that carbon to oxygen bond. The carbon at the center already has 4 bonds. It's going to let go of the weakest thing that it's holding on to, and the weakest base is the protonated oxygen. So it goes. We're going to have to remove this poster to make some space.
It's out of date now anyway.
Let me see if I'm still on screen. We'll do the next one here, because I'm not on screen anymore. I made a methanol and something with the charge. If I let this hydrogen go and give its electrons to the oxygen to hold on to as a lone pair of electrons, then I made a carboxylic acid as well. Plus, I get my acid back. So the acid goes in as the first step. and it comes out as the last step. It's catalytic.
Do you still have the method? The last step.
I made the methanol here with my carboxylic acid still protonated. So all I have to do in this right here is just get rid of that proton. But my two reactants are ester and water. My product is carboxylic acid and alcohol. So this reaction is called a hydrolysis. What does hydrolysis mean?
Splitting water.
Splitting of water. So for the additional point on this 11-point exam question now, point to the exact point in the mechanism where the water splits. I have seven sketches. Where exactly does the water split? 3. Right there. That's the hydrolysis step. Okay. Now, you can hydrolyze an ester the other way. We've already seen it. We did it on Friday. Saponification is hydrolysis of an ester, where you do this. Different arrow now. Oh. Because you're still in basic conditions. All right. So, this was your nucleophilic acyl substitution. Strong nucleophile. Direct arrow. Where's my leaving group? Charged leaving group. That's nucleophilic acyl substitution. Still the same reaction. This is subtly different. You might not see it on the surface. Every step is an equilibrium step. Because I'm in acid, everything is protonated. I have no negative charges in this mechanism. Okay. On our list of nucleophilic acyl substitutions, we can turn esters into carboxylic acids, but we cannot turn carboxylic acids into esters. What if I gave you an ester and said, and this is legit, what if the market price for esters was cheaper than acids? Well, I would take my stockpile of ester and I would convert it into acid. And then this week, Brexit and everything, it might turn out that carboxylic acids are cheaper than esters. So I'm now going to convert my esters, my carboxylic acids, into esters because they're worth more and I can sell them for more money and make a profit. With the nucleophilic acyl substitution, I can't do it. I can't go backwards because the nucleophilic acyl substitutions only have a forward arrow. This one can go backwards. If I give you the carboxylic acid, you can make the ester. You can make it. So I'm going to erase what's on the board. And then in double quick time, we're going to write it again backwards. In that direction, it's called hydrolysis of an ester. In the other direction, it's called Fischer ester synthesis. In which you take a carboxylic acid and you add acid. You protonate that acid. Weak nucleophile attacks the carbonyl. Carbonyl opens. And make a tetrahedral intermediate. I use the lone pair of electrons on one of the other groups to pick up the acid, which generates a leaving group. I then have the leaving group leave by reforming the carbonyl. Leaving group leaves as water. And then I get my catalytic acid back by deprotonating the oxygen from that carbonyl. And I just made an ester. Forwards or backwards? Okay. So there's a little bit of wiggle room here because the pKa of all alcohols and the pKa of water, they're about the same. So this is not so much of a stretch. These are equilibrium processes. If I want more ester, what do I do to my equilibrium?
You can increase these reactions.
Which one? If I want product. Le Chatelier says anything that you do to an equilibrium, the equilibrium will counteract. So if I add more reactant, the equilibrium position will say, hold on a minute, there's too much reactant, let's go make some more product. So one way to make more product, ester in this case, is to add more reactant. The question is, which reactant do you add? This reactant or that reactant?
It's both, right? You can do either one.
Okay.
Or I guess you need both to add.
The cheapest one. You add the cheapest one. Science is not performed in a cultural or economic vacuum any longer. If you can do this experiment by adding more carboxylic acid, and the guy down the street in his factory adds more alcohol, and alcohol is cheaper than carboxylic acid, then his company stays in business, yours doesn't. You add whichever one's the cheapest. Or you remove product, and there's a chance that the ester that you've made and water are not miscible, and you make 2 layers. You can siphon off one of the layers.
Wait, I have a question.
Yeah.
It doesn't affect the equilibrium if you remove water, right? Because it's just liquid.
Ah. Yeah.
Okay.
Liquid doesn't appear, the liquid water doesn't appear in the equilibrium. So you have to do something slightly more sensible than that. Okay, let's do one that's really impossible. So we know that we've got acyl chlorides at this end, and then carboxylic acid, acid anhydrides, and then esters, and then carboxylic acids. And then amides. And so everything under nucleophilic acyl substitution siphons to an amide, and there is no coming back from an amide. So under nucleophilic acyl substitution, I can turn any of these things into an amide, nice and easy. All I have to do every single time is use NH2- as a nucleophile, and every single one of them follows the same mechanism, so that SNAC mechanism, and I'm done. All right, let's do the absolute impossible. Let's turn that into this. That's impossible. Let's do it. Mechanism is on the board. It's only impossible if it's a nucleophilic acyl substitution. Group will we use here?
Cyclo, no name.
No. Let's at least pick it up a bit. Name. reaction is going to be amide plus water in the presence of catalytic acid makes a carboxylic acid and ammonia. If I substitute this amine and put any kind of alkyl groups here in place of the hydrogens, then I make either a primary amine or a secondary amine. No real difference. Okay. The mechanism that I'm about to write is the same as the one that's above it, is the same as the one that preceded it. In fact, it's perilously close to the one that preceded it, because I'm writing it from the hydrolysis point of view rather than the synthesis point of view. Yes.
So where does the water come from?
We add it on purpose. It's now way reactants. These are my two reactants. Here are my reactants. And here are my two products. And where does the acid come from? Well, I need. So the question is, okay, because I'm using water, I could just add dilute acid. In other circumstances, where this is carboxylic acid plus alcohol, should I add dilute acid to this? No. My source of acid here gets to be 1 drop of concentrated sulfuric acid. Because while it's concentrated, it's holding on to the smallest volume of water. Because water is a product in this reaction, and therefore I don't want, like Le Chatelier sees water as a product. Therefore, go make more reactants. That would be counterproductive if I used dilute acid here. This one, the more water you've got, the better this reaction works. So, here, I'm going to fake out this equilibrium to make the most amount of product that I possibly can. So I'm going to increase my reactants. Which one? This reactant or that reactant?
Water.
The cheapest one. And I'm going to presume that water is cheaper than my named carboxylic acid. Okay. So this way, this one, that can be dilute acid. Okay. I didn't do the other arrow. So this weak nucleophile attaches to that carbon. That carbon already has 4 bonds, so let's go for the pi bond that it's holding on to. And then that gives me, oh, that's nitrogen. That gives me this. Now I'm going to give the oxygen back a lone pair of electrons so that I can be this tetrahedral intermediate right here. Oh, plus I lost a carbon somewhere along the way. No. Okay. That gets me to this place. I have 5 lone pairs of electrons and 1 acid. Can And that lone pair of electrons reach out and grab this acid.
What are you just grabbed?
As would any of the other oxygens. But if I use that lone pair of electrons, then I actually push the reaction forward. So I've now protonated that nitrogen. And we have reason to believe that because this is in equilibrium, all of those things are happening at the same time. The proton is adding to the oxygen, taking a step back, taking a step back, taking a step back, taking a step forward, taking a step back, moving forward. And ultimately, hopefully there's something in there, or is there something that you do to the conditions, like give the conditions lots and lots of reactive to push the equilibrium to the right. That nitrogen has 4 bonds, therefore it has a positive charge. There's a mistake, you didn't catch it. It's now a leaving group. Let's have it leave. Give the electrons in that oxygen to hydrogen bond back. Then you make the carboxylic acid. And you give the H plus away. So it's the same for everything. It's the same. Now, technically, we're not done. I'm going to accept this. If this were a question on the exam, I'm going to accept that as being the final answer because it has described the reaction that I'm looking for. But we're not done. Why not? Why are we not done? Again, it's one of those things where you have a little bit of knowledge now, and you're looking for the solution to the difficult question, and you're not paying attention to the obvious, easy question right in front of you. Why is my reaction not finished? What's the name of my product? What's the name of my product? The name of my product is propanoic acid. Tell me one thing about propanoic acid.
It's an acid.
It's an acid. I should know that. I sure hope I don't have any base floating around its solution.
The ammonia.
Ammonia is a base. Propanoic acid is an acid. I can tell it's an acid because it's got the word acid in its name. And I know that ammonia is a base because I was awake that one day in middle school when they told us that. So have the base meet the acid and do whatever it is that bases do to acids. What happens next?
They neutralize.
What do acids do?
They accept.
They donate what?
Oh, they don't. Wait. God dang it.
I'm teaching general chemistry 2 in the summer.
God, it's been so long.
Should any of you need to just freshen up? Acids donate their H plus, and bases accept the H plus. So this ends up being, and this is going off screen so people at home, doesn't matter. That's you, Dan. Talking directly to you, Dan. I'm saying something incredibly important, and it's off screen. So you're just gonna have to find out what happened. You make the ammonium salt of the carboxylate. So technically we're not done, but you've answered the hard part of the question. Okay. All right. It is technically impossible to do that via nucleophilic acyl substitution. So let's do that as well.
Would you knock off the hydrogen that as off the propanoic acid, or do you use the hydrogen?
Well, that's actually a really good question, because I've got this floating around as well. But I've told you already that's catalytic amounts. So I would use this base to steal that hydrogen. Okay. This, so that was impossible. This one is, I know, it's going to be quick. This one is really impossible. So that was acid catalyzed hydrolysis of an amide. This is base promoted hydrolysis of an amide, and this one is super impossible. If I put amide into solution with sodium hydroxide, I do the nucleophilic acyl substitution, at which point this reaction has nowhere to go. If it wants to reform that carbonyl, it can either kick off a methyl carbanion, an amide, or a hydroxide. And the hydroxide is the weakest base, strong base, but still the weakest of those three. But if you give this reaction a little bit of time, something unfortunate happens. The base takes the hydrogen off your leaving group, so it can no longer leave. Now, when this carbonyl reforms, it chooses between carbanion, amide, or O2 minus, oxide. That's not even in our textbook because it's inorganic. So that's out of the question. O2 minus is completely out of the question. CH, whatever the carbanion is, no, it's too strong. This is now my leaving group. then I need a second step for this acid workup. Sweet carboxylic acid.
Could we make ammonia too?
Yeah. Okay, and we're done. I'm just going to put in the fine print right here that in terms of basicity of the leaving group, there's no way that the R minus or the NH2 minus is going to go. That would be hydroxide. But now, oxide, no. Okay. Off you go. See you Wednesday.
Not tomorrow.
So not tomorrow.
Nah, that does not mean not tomorrow. I'm going to look in the stockroom this afternoon because I think that our next lab is also split over 2 weeks. Keep an eye on Blackpool.